Okay, okay, okay. Thank you for joining this session about quantum chemistry and VQE with PennyLane. My name is Aoyu, and I'm an applied scientist in GSA solution team, and I'm based in Beijing. I got my PhD in biomedical engineering in Peking University, and I'm so happy to share something very interesting with you today. So let's get started. And this is the agenda of this talk. Actually, there are three parts. The first one is the introduction to quantum chemistry and VQE. The second one is hands-on session. And the last one is a brief talk about AWS open source solution for drug discovery. Let's get started the first one. So before quantum chemistry, I think we should know something about the computational chemistry. This is a branch of chemistry, and in this area, people use computer simulation to help solve chemical problems. And as you can imagine, the combination of theoretical chemistry and computer programs is mainly used to calculate the structure and the properties of molecules. And if we know the details about these basic subroutines, we can improve uh, some applications in our industries, like drug and material design. And I think that's the basic understanding of computational chemistry. And so, what's the relationship between computational chemistry and quantum chemistry? And let's get closer to the computational chemistry. It relies on theoretical chemistry, right? And has many different methods. So for the very approximate cases, it uses semi-empirical or empirical methods. For cases requiring accurate results, it uses ab initio methods. And basically, these methods are based on quantum chemistry. And actually, that's a contacting part. We need to actually, in this sense, we need to use a computer simulation to study the use of quantum mechanics within chemistry. And however, the computer time and other resources increases quickly with the size of the system being studied and the level of accuracy that we require. Just to take the simulation molecular, for instance, actually simulating this problem accurately is very difficult. The trade-off between accuracy and resource should always be considered. Just like the force fields method is fast, but it can only give you rough results. However, with this result, you can study larger group of molecules like protein, and this can be analyzed in a reasonable time. In contrast, like this method, it gives you exact solution, but it scales as a big O of n factorials. And here, n represents the number of electrons. This means that the current supercomputers can only exactly simulate around 20 electrons. In the middle, like the DFT, the abbreviation for density functional theory or Fortry fork method, it has a complexity of big O of n cube. And this still limits the number of atoms which can be simulated in this scale. And even this way, it's still not powerful enough to simulate biologics to chemical accuracy. And then let's look at this problem in a more concrete example. And just like this, the potential energy surface calculation problem. And actually, PES describes the energy of a system and especially a collection of atoms. Calculating PES is important task of quantum chemistry because the geometry of the state of atoms has a relation to its ground state energy, just like this figure shows. And in most cases, the geometry can be described as a vector of atoms, and it can be very complicated. And in this case, we consider a very simple example. Just imagine the x-axis represents the distance between two atoms, that's big R, and the y-axis represents the corresponding ground state energy. So we can draw this curve after we traverse all the possible R's. And in most cases, we care the local minimum in PS, like this equilibrium state. Because if we know this state, we can see that the molecules somehow stays in a stable state in this place. But however, as you can imagine, building this curve very accurately is usually computationally expensive because you have to calculate enough points very accurately for this purpose. And this is about a specific application of PES, bond breaking. The distance between the oxygen and that be a little bit complicated than the former case. The distance between the oxygen and hydrogen is the variable R, just like this big R. And given that R, the energy is calculated using different methods in computational chemistry. And I just name the methods here. And the different curves represent the results of different methods. From top to down, you can see that both the accuracy and the cost you have to pay for your method is getting higher. And we just see something very briefly. So there is a class of method, configurational interaction, or CI in short. It's a post-Hartree-Fock linear variational method for solving Schrodinger equation. And in this class, full CI or FCI in short, it can give you exactly numeric result, but this is very expensive. And the result is represented by the black sorted line. And okay, in the same class, CISD is limited to single and double excitation, and you can see the red dashed line is a little bit higher. And a more crude method is the CASSCF, and that's actually active. That's actually active space consistent field. And actually, this method can give the result, which is represented by the green dashed line. And still in this method, we have another method, and we name it Hartree-Fock method. And this method is usually used as a central starting point for most methods that we can use for more accurate results. So you can imagine that blue dashed line, it gives you the crude result. It's relatively fast, and it's always used as a starting point for other methods. Okay, and let's look at this problem from the point of view of the wave function, which is very important because later we will analyze more about this concept. And for FCI, so just to remember that that's the exact solution. It considers all exact states. So that's per for FCI. And you can see that it consists of many parts, but it's time consuming, right? And from the wave function perspective, you can see that the HF wave function, it only considers the first term in the expansion term of the exact wave function. But if we want to get more accurate results, we have to consider single excitations, double excitations, and many things to consider so we can get a more accurate wave function. So till now, how could quantum computer help this type of computing through some very famous algorithms like the variational quantum algorithms? And someone specific is a VQE. And to understand this problem,
we have a question from the audience. What is HF here?
Okay. HF, right? HF is the abbreviation for Hartree-Fock. Actually, that's the method. Okay. So this one is a Hartree-Fock method.
Thank you.
So in this place, I just compare different methods if you want to calculate the PES problem. And here you can see that the HF, Hartree-Fock, gives you very rough results. And I just want to describe the limitation for this method. So in terms from the point of view of the wave function. And then, okay, here, in this problem that just want to see that I just want to say that you heard me mentioning Schrodinger equation many times. So solving this equation is very important in quantum chemistry. If we have a molecular, how do we find the ground state energy? We begin by forming it as the time-independent Schrodinger equation. So this is time-independent version. And here, H is acting on our wave function. Okay, so you just see what wave function looks like, and which is a specific energy in this form. So you can consider it as a numeric value times our wave function. Then we can see that this clearly takes the form of an eigenvalue problem. because we can see that the smallest value here can be the ground state energy in this way. The expectation value of this Hamiltonian H can be calculated through measurement, right? So this format is how we measure the result expectation. And the value can be one of the eigenvalues, which all of these values are bounded by our ground state energy. So this can be considered as an optimization problem. We want to approximate the ground state energy, which is unknown, yeah, actually, by minimizing the net value, the expectation value of a Hamiltonian. We do it by parameterize the wave function, psi theta, and also our Hamiltonian H is mapped to our quantum computer because H responds to the corresponds to the system that we care about, maybe some molecules. And then, given that we model it as optimization problem, then the problem is the following question is how we can map it to a quantum computer. And the energy, right, H, Hamiltonian, can be the combination of potential and kinetic energy. We write H as the sum of T and V, and V can be considered as a function of R, small r, which is the position of electrons and nuclei. And here is the equation for kinetic energy. It consists of energy of electron and also the energy of nuclei. And this is the equation for the potential energy. And you can see three terms, the potential energy between electrons, because I use small e here, and the potential energy of nuclei, between nuclei, I use small n here, and also the potential energy between electrons and nuclei. Since they have different polarities, so there is a minus sign. And the exact solution Hamiltonian for molecular this way is complex, and we can mostly, and it's hard to solve, right? We still need some assumption because we are most interested in the electronic structure of the molecular. Given the fact that nuclei is over 1,000 heavier than electron, and also electron is also very fast, and we can invoke Biot approximation. So given this approximation, the nuclear term, the kinetic energy of nuclear term can be ignored because you can see it's relatively stopped. And also, the potential energy of nuclei can be replaced by a constant value, maybe C. And after this
Hey,
equation
how are you?
and approximation, okay,
Here's a question. What are we trying to achieve by minimizing the expected value?
uh, of yeah, I
Why
mean here
do we
maybe
want to do this?
okay. I think the reason that we want to do this because we want to solve Schrodinger function, Schrodinger equation. And given its time-independent Schrodinger equation, we can see this is eigenvalue problem, right? Eigenvalue problem. And for these eigenvalue problems, we can have many eigenvalues. And the lowest eigenvalue, we can say it corresponds to our ground state energy. And still remember that PES curve, we want, because just imagine that if we change the distance of molecules like R or vectors of R, and the molecules, Hamiltonians from these molecules will have different ground state energies, right? And in that case, we want to calculate the different eigenvalues in that setup. So we can see where we want to find the optimized parameters to find the ground state or smallest eigenvalue, which can see is our ground state energy. So we model it as a minimized problem. Is that clear? Okay.
It is. Thank you.
Okay. Yeah. Okay. Um, So after our modeling and approximation, we get a simpler Hamiltonian. However, it's still not suitable to be solved directly. We need a second quantization, and I will give some reasons for this process. You can see This is the result of second quantization. No, it's second quantization. The reason is that because electrons and nuclei are fermion. So we usually use fermion operators to describe, not this way, not the distance and the real position in the space. We use fermion operators to describe, like A dagger P for fermion creation operator and AQ for fermion annihilation operator. So P stands for the index of single electron basis function or spin metro, or spin orbitals. So this corresponds to the action of adding or removing an electron from a spin orbital. So just imagine that what we really care about is the electronic structure. So in electron structure, so we can see that we really care about how we could add or remove electrons for optimize the structure for that molecular. So this corresponds to our final purpose for this problem. And you can see that the kinetic energy of electrons and the potential energy, still remember these three terms, the potential energy of electrons and nuclei are transformed to the first term as the second quantization of the single particle mechanics. And in this part, the potential energy of electrons are transferred and the second quantization of two particle mechanics. And yeah, there's some theory behind this transformation, but beyond, but out of the scope of this talk. And later, if you could find more details about this in like multiple particle quantum chemistry, some theory books, some theoretic books. And then what's important is that the second quantization cannot still be solved in a quantum computer. We need to use quantum circuits to simulate the change in fermion systems. So to be specific, we need to use qubit operator in polystring format to describe the fermion annihilation and the creation operator. So the coefficients like HPQ and HPQS can be calculated in advance. And in this setup, the VQE is based on the Rollinized variation principle. It just means that, as I showed before, it reduces the problem of finding the ground state energy of the system Hamiltonian and to find the optimum value of our parameters for our parameter circuits. And then those circuits will be optimized using our classical optimizers in our classical computers. And let's recap the whole process in a flowchart way. Okay.
There is one question from the audience. It has been if these A and A dagger are ladder operators.
Yeah. Just as I mentioned before. So this equation, right? The first equation. So you can see my mouse. Can you see my mouse?
Yes, we can.
Yeah, we model the first equation given we are studying how electrons move in a space, but actually we want to do second quantization for describing the movement of electrons. And here these are fermion because electrons and nuclei are fermion, right? And A dagger P or AQ, they are fermion operators. So there are some rooms to transfer these descriptions to the format in the fermion operators, and this we call it second quantization. And it is important for our further transformation to transfer the fermion operator to qubit operator. Okay.
Awesome.
So that
Thank you.
may, okay. I know that there may some details in those slides. So let's recap this process in a flowchart way that may make it more clear. The first step, we can still remember that we have to define the system we want to study, and we have to construct a Hamiltonian, just like the format of the format of the electrons or the nuclei. And the second step, we have to encode the fermion operators to our Pauli operators because that's the only way those things can be run on quantum computers. Yeah. And another thing is that As we will see in our hands-on session, it's important to determine how measurements are distributed and organized to efficiently extract the required expectation value from a trial wave function, because it may cost too much resource. We should make the number of repetitions as low as possible. Then we should turn to the preparation of the trial wave function. This is done by choosing the structure of parameterized quantum circuits or ansites, right? Or ansites. And it is used to produce the trial state with which the Hamiltonian can be measured. We can use like the results of H-wave function as our initial state. As I just mentioned before, the result of H-wave function is usually used as a starting point for other more accurate results. And after that, we will measure the expression of our circuits. And the results will be used as the starting point of our optimization. The parameters of ansites need to be updated iteratively until coverage. So this requires supplying the expectation value of the Hamiltonian several times for a given parameter set. And then we can define a rule for the update of the parameters. And this rule may run many times until it converges. That is to say, we can get good parameter circuits to calculate our ground state energy. So that's the whole flow chart of the VQE. And later we can see what it looks like in our hands-on session. If we want to see it in a simple picture, so all the quantum variational algorithm, they just follow a very important idea that we need classical computer does the classical easy part, maybe running the classical optimizers for updating the parameters. And we need the quantum computer does the quantum easy part. That is to say, in that example, it's hard for classical computers to prepare and measure the expectation of parameterized circuits or parameterized wave function, but it's easier for quantum computer to do this task. So we need that task to run our quantum computers. Okay, that's introduction to the quantum chemistry and VQE. And here comes the hands-on session. Okay, in this session, actually there are two parts. The first part, I will go through the default notebook, and I believe that after you create your examples, you can open the same notebook as mine. And I will go through that notebooks, and I will review some concepts we've just talked before. And then the second part, there's another notebook with 4 tasks, and you can try by yourself. And there are 2 basic tasks and 2 advanced tasks. And at the end of this meeting, I believe that Juan will provide you with a notebook with answers, and you can check. And I believe that in most cases, there are more than one solution to the problem. So you can refer my solution, and I hope you could find a better solution for that problem. Okay, let me go through the default notebook.
I'm gonna take over for a second, Aoyu, to explain the audience how they can open the same notebook as you. There in the chat, I just pasted a link that contains the notebooks that we are gonna be using today. Our goal is to have the same screen that Aoyu is showing right now. Maybe what I'm gonna do is share my screen again, and I'll show you how this is done. I'm gonna copy. I'm gonna steal the screen again from you. Sorry, Aoyu. And screen number 2. Screen number 2. There. All right. So I can just open a browser or whatever. I paste the link. No, that's not the link. Let me see. Oh yeah, it is. No, it's not. Let me grab the link from the WebEx window. Here it is. When you click on the link, you will be basically offered to download the file directly. There's nothing that shows in the browser. I'm in Windows. I'm going to click on Save File. Goes to my downloads. I'm going to decompress it there. Open it and decompress it. Extract here. So this is my path. There are 3 files inside. This is all the exercises that we are going to use today, but the one that we are going to be using for this specific session with Aoyu is the task, the include task quantum chemistry. I suggest that you upload all your files to your notebook. So I go to Amazon Braket in the console. Then I go to the notebook section on the left-hand side. And I'm going to open my own notebook. Please make sure that it's yours. Otherwise, you will be overwriting your colleagues' work. And here, you don't need to get inside any of the folder structures. You can directly click on Upload on the top right of your screen. There. And I'm just picking my folder where I store my zip files. And I'm going to upload the 3 files. Click on Open. In Mac, obviously, this will be different. I need to click on them individually in order to confirm that they get uploaded, okay? And I have everything here. And again, as I said before, the Day 2 Quantum Chemistry is the notebook that we are going to be following now. Just need to click on it. And Aoyu is going to take you through it from here. Before I hand over to him, I'm going to check the chat in case there's any questions. If I can find it, then. As a matter of fact, I'm going to stop sharing.
So I can share right now.
You can go back and share your screen if the audience should see the same that I was just showing. Make
Okay.
it as big as you can.
Let me
take over. Yeah, just make it exactly. Thank you, Aoyu. Before you take over, let me check on the chat to make sure that everyone is okay. I want to make sure that everyone can follow. Don't worry about the time. We have time. It's more important that people follow than that we arrive through things. So appreciate your patience. Let me see. Chat window. No problem at all if you want to put everything inside the Braket example folder. The link is public. You should be able to just download it. If you are not allowed, maybe it's local permissions in your machine. It has been thoroughly tested, I have to say. But the link definitely works. Thank you, Luis. Okay, seems like more or less people are getting there. Excellent. Aoyu, your plan was to use the notebook that I shared, or you want from the?
Yeah, I think the first one I will go through the default notebook, and as long as you open the examples, you can find one, so you can run smoothly. But I want to describe the purpose of those code blocks, and I will, and that later I will show what it looks like in our prepared notebook.
Excellent.
So it's similar. Okay.
Okay, so you heard the man. He's the expert. Get into the Braket examples folder, and after that, click on PennyLane.
PennyLane, quantum chemistry with VQE. So that's the one that we is prepared in advance. So that's I will go through this experiment. So you don't have to change anything, and I want to just show what those code blocks means, and our task will based on those code blocks. So here, The first one is very important, like from quantum chemistry to quantum circuits, right? From quantum chemistry, we have to solve the Schrodinger equation. And in terms of quantum circuits, we have to use our circuits to simulate those systems and get the result that we want. So here we will see how this purpose is achieved using the following code box. So we pair some libraries, and here is very important. We use this code to know the structure of the system that we have interest. For this, we're interested in hydrogen 2, H2, and we get the symbols and coordinates. And this is important. We know what Hamiltonian is modeled, and by using this equation method, we get H and qubits. And if you see this description, actually that's our qubit operators. So you can review that in this method, it includes BO approximation and also the Fermi operators and also the encoding method. So I think you better have those concepts in mind because if you look closer to this method, you can find more parameters to set. And then after that, you know that the Hamiltonian, the Hamiltonian decides how we measure our system. And this tutorial, it also want to compute the total spine. It can get the SC, S2 in this qubit operator format. And this will be used as observers. And later we will see where we will put those results. And so here, with these functions, we will design our answers, right? And here, use this sentence or this method to prepare our HF asset state, just as I say in our presentation. And you can see that for these specific ansatz or single doubles, and also for this circuit, you have to prepare the single and double excitations because this circuit needs those values. And with this sentence, we can prepare our circuit. Okay. And after that, if we want to use the PennyLane to run our circuits, so we have to use the QML device to initial our DEV, that variable. And here, actually, we design two circuits, right? This circuit just comes from a definition of all singles doubles. But interesting is that we want to measure the different, we want to measure the circuit in two different ways. The first one comes from the molecular Hamiltonian, and the second one comes from the spin 2. So this actually decides how we observe our circuits. And then here given the definition for spin 2, we have to use this codes to transfer to the value we really care about. Since this we have our parameter circuits, so we have to define the theta or the parameters we want to learn, and this is used to initial the theta. And with this initial theta, we can find the initial value for energy and spine. You see, it's not that perfect, right? So that's the reason that we have to put in a loop that combining the quantum computer and classical computer for optimization. And here, after all the preparation, we can go to the stage of minimizing the energy. And if anyone was familiar with machine learning, so you can see that PennyLane also has the similar optimizer, classical optimizer, that gradient descent. And it also has a step size like the 0.4. And also you can see it's similar to our learning rate. And we have this optimizer. We have to define how many iterations we want to use to run optimization. And in this function, you can see after you run this in function, it will continues to optimize our circuits given the outputs of energy expo. So this comes from our observers defined by the molecular Hamiltonian. And we want to this one be as small as possible. So we can see it continues to optimize this output, right? It finally gets the stable value. And according to this description, this stable value is pretty close to the ground truth and in a very in a very accurate degree. So this you can also use this color block to draw the draw the trend of this optimization, both for energy and the total spine. Okay, so that's how we run our whole process. Did you still remember that flow chart that using uh, our VQE basic functions? But what if we want to run it in our like real QPU? So we have to add the parameter that is shorts because we have to measure many times and in order to get a more accurate results. And here we have, in this place, we have to care about the strategies of measurement. That is to say, we have to use as small shots as possible to get the accurate results. And here, let's introduce the concept of the measurement grouping. So in this place, you can see that some measurement operators are grouping together. So that is to say, with this function, we can use few circuits with many measurements to save our cost and also get the good results. Luckily, PennyLane has the built-in method to do this function. So if you want to measure the results in QPU, that is to say, if you want to repeat the flow before with some shots, you better use the compute grouping so you can save your time and costs. And just like this, after compute group, still the similar process, right? Energy expo and S2 expo, and then still the similar equation. And you can see it runs smoothly with the shots. And then we can also get the good optimization result. So that's the go through of the whole notebook. And I suggest
There
that
is a
you run
question
many
from the
times.
audience.
Okay.
Is there a concept of early stopping, like in traditional machine learning for steps, where the benefit in the optimization is lower than the threshold value?
Okay. So you see that you want to do something like an early stop to stop optimization if your noise is small. Did I get that correctly?
That is correct.
Yeah, you could do that, but I think this is a very simple problem. You don't have to worry about this problem very seriously. But if you want to do a very complex optimization problem, you can use something like early stop or other mechanisms to save your time. Um, yeah, sometimes if you try different ansatz or different molecular Hamiltonian, you will find it's not easy to optimize to the ground state energy. So in that case, you may try some tricks for optimizers. And I think you can do experiments in the notebook that I prepare for you. So I hope that answered that question. Okay.
I think it
So
does.
actually, okay, oh, see, okay. So this is the notebook that I prepared for you. Actually, there are 4 tasks. The first task is pretty easy. I just suggest because you can find a, a folder here, and there are different files for H2 in different structures. So I suggest you just change the files for different structures, and you can see that what it looks like. Actually, you cannot tell it exactly. It's not intuitive, but I think this task is left for you to change the files for different structures. Okay, so that's the first task. And the second task, as I just mentioned before, you can choose different types of answers. Here, I leave a link for you. So in our original notebook, you see that it's all single circuits, right? It's prepared here, all single doubles. It's a kind of ansatz. And here, actually, you can change another ansatz because there are many ansatz and tablets available here. And I paste the link for you. So maybe you can try replace the ansatz with this one. Okay, so that's the second task. You can try to change the ansatz and also run the foreign code box to check whether it works. Okay, that's the second task. And the third task may be a little bit tricky. So I I guess that you still remember the potential energy surface, right? That curve. And after traversing all the possibilities of R, and for each R, we calculate the ground state energy, and then you can get this curve like me. And I draw this curve myself. If you put the similar value here, you can get the similar image. But I want you to loop all the files inside folder and also repeat that process of VQE. And then after that, I think you can get this curve. So that's the third task. That's a little bit tricky. And the last task is that so OpenFermion is a very famous library to work with quantum chemistry. So what if we have some data prepared by OpenFermion? Can we transfer it from the OpenFermion to the PennyLane process? Then we can continue to use the process we have just learned before. So I have prepared the codes here. So the thing that is you have to prepare the H Hamiltonian and the qubits from the data like prepared by OpenFermion. So OpenFermion. So that's 4 tasks. I think you can try to take some time to try, or maybe we can provide the notebook with answers later, and you can check and offline. Maybe the
Okay,
first 2 tasks.
there is a couple of problems. It's a lot to take, so probably we will need one by one. But there is a question: Do we need to put this notebook inside any folder? Because it seems like people are missing a folder dependency in one of the
Okay,
steps.
okay, sure, sure.
It's the QChem folder.
So it's in this place. It's in
Right.
the
I
quantum
see what the
chemistry
folder
with
is.
VQE.
So you see the
You
path
should.
there, Rolando and others. If you go inside Braket examples, then PennyLane, and then folder number 3, that is where you have to put your notebook, not in the root folder as I initially did it. Apologies for the confusion. The next thing, if you can maybe just put the task number 1 there and let start people going through it. And when they are ready, they can tell us here in the chat to move to task 2 or to scroll down or whatever they want. But I think it's good that we give them a few minutes to play around.
Yeah, just to take some minutes to finish at least task 1 and 2. Yeah, task 1, I think it should be easy. Just like how can you get the symbols and the coordinates for the system that we have interests.
Excellent. Let's do something. Let's switch back to the presentation because they already have the notebook and they can see it themselves.
Okay.
And we leave the presentation there fixed in the screen.
Okay. Let me switch to the presentation. Swap. So can you see my screen?
Perfect. Thank you.
Yeah. So just as I mentioned, I go through the default notebooks. I hope you could find the concepts that we just learned in the code blocks. And there are 4 tasks, and I hope you enjoy playing with those codes. And okay, here comes our last session, which is very short.
No, hold on a second. No. Let's give them a couple of minutes to play with it, and then we'll share the solutions notebook, and after that you can go to the next one.
Okay.
Don't worry about the time. We can stretch a little bit the next session. Please feel free to ask any question, guys, if you have any question in the chat.
So it seems that someone cannot load his notebooks.
Yeah, I'm gonna remind the instructions in text here so everyone can follow.
Yeah, let me just
Should
let me show that again. Just oh, sorry, I should share. So what I'm doing that I opened the folder here, right? It's the quantum chemistry with VQE under the PennyLane. And there is a default notebook with the name 3 quantum chemistry with VQE. And it's prepared in advance. And in this notebook, 3 quantum chemistry with VQE, I go through the code box to see where exists the concept we've just discussed before. And after that, I think it's day 2 quantum chemistry notebook. Sorry about that. You may have different name here, but actually it's the same thing. And I will leave 4 tasks for you, and you can find the place to input your codes. Maybe this is for task 1, and this is for task 2, and also we have the space for task 3 and a task 4. So I hope that makes it more clear.
I will share it just 1 second, the solutions.
Okay.
Sorry if you don't have, guys, access to your local device, or there is some restrictions in the network. There's not much we can do about it. That's the zip file with all the notebooks. Now I'm gonna share the solution if you want to check it on your own time, or if you are curious about how to finish the exercise. Here is the link. Some firewall companies detect the notebook as something dangerous and actually block it. Sorry about that. After this session, for those of you that are still asking the question, we are going to share the recording, the presentation, and the notebooks. That will be sometime in September after we review everything. It will be available for you. The floor is yours, Aoyu.
Okay. So actually, since Pen has just given you the link, I will give a brief talk about this open source solution. You can always find it in our GitHub solution library. It's an open source solution that allows researchers and quantum computer elevators, and just as you guys, to design and run computational studies in the field of drug discovery. So as you can imagine, Amazon Braket is just one of many AWS services. So it's important to integrate Amazon Braket to build some powerful solution in the cloud. And this solution provides you with 3 benefits. It's a hybrid architecture. It provides you with flexibility to use different computing resources, like AWS Batch for classical computing and Amazon Braket for quantum computing. And it provides you also with some notebooks to learn the drug discovery use cases, like molecular unfolding or molecular simulation. So you can see the details in that link. And also it provides you with a dashboard for visualization. In that dashboard, you can see the difference between quantum computer and classical computers in a more clear way. So actually, that's the basic introduction for this solution. So if you had any interest, you can contact us. We can give you a more detailed talk about this solution. And actually, okay, that's the end of my session. And thank you for your time. And please take the survey. And also, I put the survey in our notebooks. And also, okay, someone raised the hand.